Okay, so we are on day 2 of chapter 10, section 2. Okay, we are continuing with inference tests for the difference of two means. Today we're going to be working on one that's an experiment. Okay, and then we're going to talk about doing a confidence interval for the same thing, same kind of thing, a difference of two means. And then I'm going to give you a problem to take home tonight. It's actually in the notes I already sent you. It should be the last page. Where you're going to run an inference test, state, plan, do, conclude, and then you're going to do a confidence interval at the end to prove that your answer is correct. Okay, so let's go ahead and get down to this and start picking out the information that is important. And this is what you should be doing on open response questions. Go through, read, circle the stuff that's important that you need. Okay, so does increasing the amount of calcium in our diet reduce blood pressure? Well, right there, something kind of important, because that might be something you could put in your conclusion. Okay, so the researchers, because that's what you're trying to prove, the researchers who worked to answer this question found that the strongest relationship between calcium intake and blood pressure occurred in black males, so they designed another study with an SRS that takes care of our random, right? And 21 healthy black males, that's going to be part of our independence check. Okay, and then 10 took a calcium supplement, so that is our treatment group, and 11 took a placebo, so that is our control group. Okay, the response variable being tested was the decrease in blood pressure, so that kind of tells us how our HOHA is going to be written as far as our alternative. Okay, if you're wondering which group is which, I'll count them up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That would have to be our treatment group, and we're going to call that mu1. And this is our control group, and we're going to call that mu2. Okay? And you can write on your open response like this. The people who are grading it are not going to take points off if you've written all over the question and underlined and highlighted and done whatever you needed to do so that you had all the information that you needed. Okay, and if you're worried, yes, you can actually have groups that are different sizes. That is perfectly okay, because your calculator is going to, find the mean of them anyway, and it doesn't matter how many are in there. Okay, so do the data provide sufficient evidence? That's our clue that we are running an inference test. Okay, to conclude that a calcium supplement reduces blood pressure more than a placebo. Okay, so that means the treatment works better than the control. That's what we're trying to prove. All right, so let's go ahead and jump in. Your state. Well, your null is always that there is no difference. Okay, and then we use the alternative as a test of what we're trying to prove. If the treatment group works better as far as taking the calcium truly does reduce their cholesterol more, then these should be bigger numbers and these should be smaller numbers, right? mu1 should be bigger, so that's going to be greater than 0. Okay, so it kind of does tell us our direction that we're going to need to do. All right, so let's define our variables. mu1 is the true mean reduction in blood pressure, right? Because that's what they're actually testing with calcium. Okay, and mu2 is the true, I forgot the word the on the first one, is the true mean reduction in blood pressure with placebo. Okay. Now, you could write these together, but you'd have to be really, really picky about the wording, and it would be something, let's move this down. It would be something like, let's see, mu1 minus mu2 is the true difference. You have to put the difference first in mean reduction of blood pressure calcium minus placebo. And that would be fine. We could write it that way, but you have to be very, very specific on how you are phrasing it. You have to put true difference in mean. You need to quote what it is you're checking, and then you need to make sure, or what you're testing for, and then you have to state which way you're subtracting. If I define them separately, it's obvious they're being subtracted, and which way they're being subtracted, because I've already defined mu1 as the calcium and mu2 as the placebo. So just be really careful. You don't want to lose points just because you didn't define your variables correctly. Okay, plan. Random independent normal. Good news. We were already given an SRS, so we're fine. Independent. This is where we get to combine our two treatment groups back together because they really were pulled from, what do you want to call it? They really were pulled from one population. Okay, so there are more than 21 times 10 healthy black males in the world. No problem. Okay, normal is a problem. We cannot, number one, graph them together. We can't graph all 21 together. It doesn't work that way because they were split into two different treatment groups, okay, a treatment and control. We're going to have to do a histogram for each one. One for the group of 10 gentlemen and one for the group of 11, okay? So in order to do that, you're going to need the mean and the standard deviation. So you really should, already have your calculator be putting the data in. I went ahead and saved it for myself because otherwise I would lose my mind. But we're going to make a histogram, okay, of the two sets of data. And keep in mind, I don't have my graphing calculator with me. So the only thing that I can do is I can figure out what the range is and divide it by the square root of n. I can do that, right? And then I can, put my bins in there. So my range, goes from 18 to negative 4. So my range is 22. And 22 divided by 10 is 2.2. Okay, that makes life easier. 18 minus 5. So that's 2.3. All right, so I need to go from negative 6 to 19. Okay, so that means I'm actually going to be on the other side. That's like negative 6 to, if I'm going to add 2.3 to that, it's like negative 3.7. And then, actually, you know what? Let's make this just a tad bit bigger so I can figure out where everything is going to go. And I'll just move the do down. Okay, so I know I need to go from negative 6 to positive 19. Okay, so that's like negative 6 to, I think it was like negative 3.7. And the next one, if I add another 2.3, that's going to be negative, 1.4, negative 1.4 to, wait, no, hold on. Sorry, I don't think my range is quite, it's not the range, sorry, it's the, divide by the square root of 10. Never mind. 23 divided by the square root of 10. I'm having moments. I'd be here forever. Okay, so the 7.27, so I'm just going to say 7. Okay, so I have to go from negative 6 to 19 by 7, basically. All right, so negative 6 to 1, and then 1 to 8, and then 8 to 15, and then 15 to 22 is basically where my bins are going to be. Okay, so that's going to be about right there then. Okay, so I just need to count how many are in each group. Negative 6 to negative 1 in the first group. 1, 2, 3, 4. Okay, so 1, 2, 3, 4. And again, if you do this on your calculator, this is pretty much what it's going to come out to. All right, let's see, from 1 to 8. 1, 2, 2. Okay. 8 to 15 is 2, and then 2 in the last group. Okay, so this is my first group. This is the treatment. Okay, so now we're going to do the control over here. And again, put this in your calculator. You should already have your histograms done. You should not be waiting on me. All right, so let's see. Highest minus lowest for this one. My range is, looks like 12 minus negative 11, so it's also 23 as far as its range. So 23 divided by the square root of 11 now is 6.9, so I'm just going to call that one 7 as well. Make life easier for me. And it has to go from negative 12 to 13. All right, so you're just going to have more on the negatives. All right, so that's going to be negative 12 to negative 5. That's going to be negative 5 to 2, 2 to 9, 9 to 16, and that should do it, right? Yeah, and then the negative is going to be right about here. Okay, so how many are in the group from negative 12 to negative 5? 1, 2, 2. All right. 2, 3, 4. Okay, how many are in the group from negative 5 to positive 2? 1, 2, 3, 4, 5, 6. All right, that's a little bit higher. Okay, from 2 to 9, 2, and then 1 in the last group. So 2 and 1. And again, this should look similar, if not exactly, because of the rounding issue on mine. And I'm just doing this literally because I don't have my graphing calculator with me. It's kind of fun. So we have our normal, and there's no gaps or outliers, right? So we can say that these are approximately normal, or normal enough, if you want to put it that way. Okay, so but what we're checking at least is, really for gaps and outliers, because that's the big no-no. You just can't have those with the t-distribution. Okay, it can't be dealt with. Skewness, a little bit of skewness is okay, but gaps and outliers are bad. Okay, so the do. All right, so the do, as far as the formula, same thing that you've been doing. It's basically a probability test, and it's t equals rather. What you should be subtracting would be your sample means minus your population means divided by that really big square root that we talked about yesterday. And that's going to be s of x1 divided by n1 squared plus s of x2 squared divided by n2. All right. So what that setup looks like in the real world, if you've already run the data, then you should know that your two means are 5 and negative 0.27. So 5 minus negative 0.27 minus 0. Oh boy. And I rounded my standard deviations for this, so I may end up getting a little bit more error here. But 8.74 is the first one. All right, so 8.74 squared over 10. And that's going to be over 11. And the other one is 5.90. Okay, so again, depending on how you put this in the calculator, you may get a little bit of different answer because you're probably having your calculator hold your decimals for you. I'm going to go ahead and do this in my Desmos one. We'll see, where we come out with. So 5 minus negative 0.27 obviously is just 5.27. That's no big deal. Oh boy, the big one. All right, square root of 0.74 squared over 10 plus, don't forget that you are always adding your standard deviations together, never subtracting, squared over 11. Okay, and I'm getting 3.29 rounded for my standard deviation combined. Okay, 3.2868 and a whole bunch of other stuff. So 5.27 divided by 3.29 gives me 1.6. Okay, so I just need to check real quick. Go back up. We are doing a greater than. Okay, but for a t-distribution, that doesn't really matter. We don't actually have to you know, subtract from 1 or anything like that for a t, but just making sure. So, all right, so what we're looking for is the probability that our t value basically is greater than 1.6. Okay, and remember that we have 2 groups, so our degrees of freedom is based on the lowest. So I have 9 degrees of freedom, and I want my t value to be greater than 1.601, whatever it is. All right, so go to your t distribution, 9 degrees of freedom. 1.601 is somewhere between 0.05 and 0.10. And both of those are greater than an alpha of 0.05. You know, because 0.05 is not, you know, we're not allowed to do an equal to. All right, so my p is greater. The probability of getting basically these 2 samples, right, given that the null is true, my probability is somewhere between 5 and 10%. Okay, so that means we fail to reject, right? We do not have sufficient evidence or enough evidence, however you want to phrase it, evidence to conclude what? All right, so this is where we get the interesting part. To conclude that increasing the amount of calcium in your diet reduces your blood pressure if you want to throw context right back at them, which would be good, okay, because that's really what we're trying to prove. You can also state that we do not have sufficient evidence to conclude that the true mean difference, or the true difference rather, in mean reduction of blood pressure calcium minus placebo is greater than 0. That's fine. And that's literally taking your definition of your variables and throwing it right back in your conclusion. But knowing what we're being asked, and technically it's an experiment, so it's cause and effect, we don't have sufficient evidence to conclude that increasing calcium decreases blood pressure. So we have our cause and effect stated. And, you know, increasing calcium being the cause and blood pressure, or decreasing the blood pressure, being the effect. Okay, so we don't have evidence for that. All right, and that is from top to bottom how you would run a difference of means for an experiment. I mean, just like we did last section, we did a difference of proportion for an experiment. Okay, so real quick, this is, you know, very short as far as the video goes. I want to make sure you don't forget how to run a confidence interval, and I'm sure you don't. Okay, our test statistic is still x bar 1 minus x bar 2, right? Standard deviation, that should be, you know, s of x bar 1 and s of x bar 2, because we don't know what they are. The t critical value is still based on the level of confidence and the lower of the 2 sample sizes. Okay, so I just want to, you know, prove to you. All right, so let's do a 95% confidence interval. So my test statistic as far as setting it up, and I'm not going to do the whole state plan to conclude, although for state we are estimating the true difference in mean. You know, you can define them separately, but you need to state that you're estimating the true difference in mean. All right, so the actual statistic is 5 minus negative 0.27 plus or minus, well, what is a t critical value for 95% at 9 degrees of freedom? Okay, 95% at 9 degrees of freedom, I'm getting 2.262. 2.262 times, oh boy, let's see, 8. Okay, so 8.74 squared over 10 plus 5.90 over 11. Now, I already know what I got for the standard deviation because I saw that already. And that was like 3.29. Okay, so basically it's 5.27 plus or minus 2.262 times 3 point, and again, depending on how you either put this in the calculator or carry your decimals out, because if you carry them out further, you're obviously going to get a more exact answer, and that's fine. If you only take them out to 2 decimals, your answer is still going to be considered acceptable. They understand as long as you round correctly. 0.2868 times 2, whoop, nope, 2.262. Okay, and again, I'm doing this by hand with the Desmos calculator. You should be doing this quite a bit faster than I am. All right, and oh, lo and behold, 0 is going to be in the interval. 0.27 minus 7.4347. Oh, that's definitely in the interval. Negative 2.1647 and 5. Okay, 5.27 plus 7.447. 12.7047. Okay, so what we would make as a statement to this, being that it's proof, since 0 is contained in the 95% confidence interval, and if we did a 90%, which is technically what we should have done, right, since we did a one-sided 5%, this really should have been a 90%. This makes it narrow. It kind of proves it even better, because it means we would be comparing our alpha. We could do an alpha of 2.5% instead of 5, and you know we've already proven that it still works. I mean, obviously our p-value was high enough to cancel at just about anything unless we decided to take an alpha of like 10. Okay, so since 0 is contained in the 95% confidence interval, that basically means having no difference in reduced blood pressure. And you can keep this as far as for your problem tonight would be a good idea. Since 0 is contained in the 95% confidence interval, having no difference in reduced blood pressure is a possibility. And therefore, we fail to reject. Okay, so, and just like that, as far as if 0 is contained in there, then, then that means 0 is a possibility. If the problem I give you tonight, 0 is not contained in the confidence interval, well, then you should have rejected. And you would say that. You would say, since 0 is not contained, then not having a difference is not a choice or is not a possibility, therefore we reject. So you can actually state it that way, and it works out very nicely. So again, the last page from your notes today deals with baby walkers, right? And it's got all of the stuff in there. The good news is that both of your sample sizes are big enough to where you don't have to do a histogram. Yay. And they give you the mean and the standard deviation, so you don't have to worry about, doing those. You just have to worry about actually, setting up everything. And yes, please do a confidence interval to prove it at the end with the statement. Okay? Take it easy. I will be back teaching live tomorrow, and then you'll be able to ask whatever questions you need. You should be continuing to read Section 2, again, going over the vocabulary, and I will be giving you some problems from Section 2 tomorrow after the live lesson. Take it easy.